So it's like about a month into continuous and like struggling for a job. I'm interviewing for Martinside Inc. So they're a materials company, so that's gonna be pretty good. I don't want to work as a camp counselor, so I need any job though.
Steven?
Yeah.
Nice to meet you, Patrick.
Nice to meet you, man.
What's with the camera crew here?
Oh, it's for a project. Great project. Lots of learning, but
All
you
right.
know,
Well,
it's gonna happen.
I guess we can just jump right into it.
Alright, Steven, so here at Martinsite Incorporation, what we're looking for this position is a co-op student who understands the control of properties of materials. So today we'll be doing a technical interview where you will be choosing an appropriate material for a given problem that I will provide for you.
Cool.
So more specifically, we're looking for someone who's capable of performing a material selection process using the CS UDUPAC. I'm not sure if you've used that software before, but so the material is going to be for a given design and function. So you should be able of identifying potential issues or environmental degradation that can happen to the material, and accordingly you should determine which strengthening process or heat treatment, if any, is required for the material. Does that sound good?
Cool. Sounds like 230 prepared me really well for this
Yeah. Okay,
interview.
so here's an image of the part. We've had that printed out for you.
Cool.
So this is a grade crossing signal. So this brings down the arm whenever a train is approaching.
Right.
And so what we want you to do is find the appropriate material that will be used for the shaft right here. And this will be supporting the counterweight and the arm system itself. So to start you off with an easy question, what do you think the intended operating environment would be for this part?
I'm assuming since you're a Waterloo company, it would be in Waterloo. So Waterloo, temperatures range say from negative 40 degrees Celsius in the winter to 40 degrees positive in the summer.
Mm-hmm.
So definitely has to deal with rain and snow and maybe even like hail. Since it's a great crossing signal with a really tall pole, then it might have to deal with a lot of wind and maybe vibrations on the train. So quite a few things there.
Alright, that sounds good. So now walk me through the process of how you would find an appropriate material for this part. So the part itself, it has a length of 863 millimeters and a radius of 16.5 millimeters. In order for it to fit into our existing system, we're going to need you to remain in these dimensions. So these dimensions are going to be fixed. So also the weight of the counterweight and the combined arm was calculated to be around 240 kilograms.
Okay. Cool. So first, since there's a restriction for volume, then I would want to be able to have a certain strength in the material. So the Young's modulus has to be a certain amount. And since you're like a company and you want to make money, then cost, you want to keep that down. So
Absolutely.
you probably want to optimize for cost.
Mm-hmm.
So if we just calculate the the minimal amount of GPA for the Young's modulus should be, say, 180 gigapascals. So there's that, and then we have the cost per unit. So say $2,000 would be the max. So the cost per unit would be, let's see here, $2.7 million per cubic meter for the max there.
Okay.
And then if we plug those two in to make a MPI line, then that should give us these lines over here. And cool. So I loaded up into the CES like you said,
Okay.
and I got these three lines for the
Okay.
minimum Young's modulus, the maximum cost, and the MPI line.
I see.
So if we want to minimize cost, then the material that would be chosen would be cast iron white. So it's a low alloy, but over here it looks like it'd be too brittle, so it'd be hard to manufacture. So from what I know about making gear shafts and the types of steels, then 1045 is usually the common steel that's used. So and it's still relatively cheap, so I'd probably go with 1045, even though with the EDU pack they would use cast iron because it minimizes costs.
Okay, that's very impressive. So now using this 1045 carbon steel, would there be any heat treatment techniques that you would recommend in order to use it into the system itself?
So 1045 is a generally medium carbon steel, so it's probably not too soft. So you could probably anneal it to make it a little bit softer.
Yeah.
Since with this you don't want to catastrophically fail, which so you don't want any brittle materials. So by annealing it, you'd be able to make the shaft a little bit more ductile. So when you anneal it, you increase the temperature to maybe 800 to 850 degrees Celsius, and then because it increases or it gives it activation energy, so then internal stresses and the grains would grow, and it would just make it more ductile and less likely to just brittly fracture, and probably more appropriate as a material for this shaft.
Wow, you knew that all by yourself?
Well, my mom worked as an annealer, but I learned most of the things I know from ME230 with Professor Kwan.
Oh yeah, I've heard good things about that man. So now since this part has been strengthened, what steps would you take to prevent corrosion, since that's such a common occurrence with steel?
With this part, I'd most likely do zinc plating. So zinc plating uses zinc as the sacrificial anode in, I guess, the system of the shaft. So then the zinc would corrode instead of the iron in the shaft. So zinc's pretty good because then it reacts with the air to create zinc oxide, and then it reacts with water in the air to form zinc hydroxide, and also reacts with the carbon dioxide to form zinc carbonate. So it makes it significantly more corrosion resistant than if you just had the 1045. To make the zinc plating, you'd want to use electroplating. So you put the part, or the shaft in this case, into a barrel of electrolyte, and you'd send current through, and from the anode, which would be the zinc, the zinc molecules and zinc ion, would go onto the part, and then it would plate it. You'd rotate the barrel and the part while doing the plating, so it makes it a little bit more even. And then once you're done, you want to clean it up and make sure that your part's good, and the zinc would be good. Oof.
Wow, did you memorize all that or what?
My dad used to work as a zinc coater, but ME230, great course.
Oh, that's very interesting. So yeah, that concludes about our interview for now. Do you have any questions maybe that you have?
When can I start?
Oh yeah. Well, we still have to interview the other candidates, but it was good interviewing you.
Good interview.
We'll maybe stay in contact.
Maybe.
Unlikely, but you gonna leave your mic?
Oh yeah, I definitely aced that interview.
To reiterate, once the material selection process is complete, the manufacturing process would be as follows. First, the 1045 carbon steel would undergo strain hardening to increase the overall strength of the metal to yield a greater safety factor. In this process, a stress greater than the yield strength would be applied to the sample, causing dislocations to move and additional dislocations to form. The tendency for dislocations to get tangled or pinned with one another increases as more form, which also decreases their mobility and leads to a stronger material. This type of strain hardening is called cold working, as the atoms are unable to rearrange themselves at lower temperatures. Next, annealing will take place to eliminate the undesirable effects caused by cold working, such as the loss of ductility and the formation of internal stresses. For 1045 carbon steel specifically, annealing can be completed by heating the metal between 800 degrees and 850 degrees Celsius and holding it there until uniform temperature throughout the metal is reached. Once this is achieved, the furnace should be turned off and the metal should be allowed to cool. The resulting metal will have increased ductility, making it more machinable. Next, the shaft can be formed, with a length of 863 mm and a radius of 16.5 mm. The shaft can be coated with zinc through electroplating. As mentioned before, this would aid in protecting the shaft from corrosion, which would ultimately increase the lifespan of the metal and its functional environment. Lastly, the shaft is ready to be installed into the grade crossing signal.